For students learning the fundamentals of chemistry, their most powerful rule of thumb is the octet rule. Every element has a certain number of valence electrons in their outermost shell, but they are most stable when they have 8 of them, corresponding to a completely filled valence shell. Because of this, atoms may take, donate, or even share electrons to achieve that stable octet. These interactions are what lead to the formation of molecules, ions, complexes. They are the essence of chemistry. However, there is one group on the periodic table that already has a complete octet in their neutral state, the noble gases. These gases, therefore, are already stable on their own. They don't readily form bonds, they have a high ionization energy, and by extension, they have weak intermolecular forces. For these reasons, the noble gases don't get a lot of discussion in Gen Chem, which may lead students to assume that there just isn't anything useful or interesting about them. But that isn't really true. In fact, the study of noble gases is a rich field that tests the boundaries of our present understanding of chemistry. And if you stick around to the end of this video, you may find that the noble gases are more interesting than you might think. The first dilemma one faces when trying to study noble gases is finding them. After all, these atoms don't readily react or form solid compounds with other elements. Because of this, it took a long time for scientists to even discover the noble gases. The first of them was found not by isolating the element here on Earth, but instead by looking to the Sun. When looking at the emission spectra of the Sun, astronomer Pierre Janssen discovered a bright yellow wavelength corresponding to an unknown element. He named this new element helium, after the Greek word for sun. It turns out that the emission spectra of noble gases have a wide range of vibrant colors in the visible range, which is why one of their most common usages is neon lights. Due to their difficulty to observe, the noble gases were once assumed to be very rare, but that's not actually the case. Helium is the second most common element in the universe, and our atmosphere has more argon in it than CO2. That being said, isolating these elements can be a challenge. Helium is found in some natural gas deposits created from radioactive decay, but the other elements have to be extracted in trace amounts from the atmosphere. This is done by cooling and compressing the air into a liquid, and separating the noble gases with a low temperature distillation. The inertness of noble gases has many practical applications. They can provide inert atmospheres where other gases would cause unwanted chemical reactions. The one you're likely most familiar with is a light bulb. Now, unlike in neon lights, the emission from a light bulb actually comes from this metal filament when it's heated up. Now, if exposed to the surrounding air, the metal would quickly and violently combust with oxygen. But within this glass container filled with argon, our metal can heat up and glow without being consumed. The noble gases also make for good cryogenic refrigerants, thanks to their low boiling points. While the noble gases do have a very stable electron configuration, their electron cloud is still sensitive to the polarizing effects of other atoms. Under special conditions, these noble gases have been found to form a variety of different bonding motifs, ranging from fragile van der Waals adducts to true covalent bonds. So how do you create a molecule with an element that doesn't want to react? Your best bet is to use the most electronegative element on the periodic table, fluorine. Its electronegativity making it the most capable at pulling away those valence electrons to form a bond. The reactivity of the noble gases increases down the periodic table as the electron cloud gets larger and the effective nuclear charge gets weaker. Radon is prone to radioactive decay, so the best noble gas for reactions is actually xenon. At high temperatures, xenon reacts with fluorine gas to form xenon fluoride compounds. Different fluoride molecules can be formed depending on the ratio of the gases as well as the pressure and temperature. Other noble gases can also react with fluorine in a similar way, though krypton is the only other element that reacts in macroscopic amounts. From these fluoride compounds, scientists are able to form bonds to other atoms that wouldn't be able to react with a noble gas directly. For example, using xenon difluoride, chemists have been able to form xenon bonds with nitrogen, as seen here. Xenon can also be incorporated into organic molecules through the substitution of boron. Another reaction of note is a metathesis, where xenon hexafluoride reacts with water to form xenon trioxide and hydrofluoric acid. Noble gas compounds are usually powerful oxidizers and highly reactive. Xenon trioxide is no exception. It will decompose explosively if disturbed. But chemists at McMaster University have been able to form complexes of xenon trioxides with coordinating ligands such as crown ethers, which remarkably made the compound stable at room temperature. Other noble gases are more difficult to form covalent bonds with atoms other than fluorine, but they can be incorporated into coordination compounds. The first of these discovered was tetraxenogold, created from the reduction of gold fluoride by a strong acid in elemental xenon. It consists of gold surrounded by 4 xenons in a square planar formation, though triclinic and tetragonal geometries have also been found. This complex can also be formed with argon and krypton. Another reaction forming a noble gas complex is shown here, where M can be chromium, molybdenum, or tungsten, and E can be xenon, krypton, or argon. To form these complexes, the noble gas must be in a liquid or supercritical state, and they are also often short-lived. The chemistry of noble gases under normal conditions is rather limited. However, in one field, they've become a primary group of interest, and that field is chemistry under high pressures. Under extraordinary pressure, millions of times stronger than our atmosphere, the chemistry of noble gases becomes increasingly bizarre. Under standard conditions, a noble gas's highest occupied molecular orbital is of course completely filled, and the gap between it and the lowest unoccupied molecular orbital is quite large. This makes it, like many other nonmetals, an insulator. However, under extreme pressures, this gap is compressed and becomes narrower, eventually to the point that electrons can freely move between the HOMO and LUMO. In these conditions, the noble gases actually adopt metallic properties. They conduct electricity. They respond to magnets. And that's not all. Under extreme pressure, the energies of their valence orbitals increase, causing previously inert gases to become strong reducing agents. This discovery may have provided the answer to a decade-old scientific mystery. See, based on the kind of meteorites that formed this planet, the amount of xenon in our atmosphere seems to be much smaller than it should be. Similarly, the amount of argon we'd expect from radioactive decay of other elements is also smaller than expected. It seems as if a large amount of these noble gases is missing from our atmosphere, a situation which had the scientific community perplexed. However, it was discovered that under extreme pressures, similar to the Earth's core, the noble gases can be oxidized by iron and nickel and form solid compounds. This suggests that the Earth's core may be a reservoir for our missing elements. Similarly, scientists have also confirmed the existence of helium hydride in interstellar space, which is theorized to be one of the first covalent bonds to form after the Big Bang. So, the study of noble gases offers us unique insight on how the rules of chemistry change in some of the most extreme environments of our universe. I hope this video has inspired an appreciation for a group of elements that aren't typically in the spotlight. While the noble gases may seem boring on the surface, they actually pose an exciting new challenge for modern chemists. They present us the opportunity to study processes that seemingly contradict the logic of chemistry, and in resolving that contradiction, they may actually enrich our understanding of the universe.